How's it going? This is Will Sutherland doing Lab 4, Oscillations. So the purpose of this experiment was to predict the motion of an oscillating mass attached to a spring and to determine whether the energy principle was upheld. Our system was the mass and the earth and the spring, and the surroundings was just everything else. So the results, we found that the energy principle was satisfied by the model, and the periods of oscillation were different for the x positions and the y positions, suggesting that the spring constant had a different effect in each direction. So there were two fundamental physics principles used, Newton's second law and the energy principle. Newton's second law, we know F net equals mass times acceleration. Within that, there were two main forces, the force of gravity and the force of the spring. Where the force of the spring is just negative k. K is the spring constant. S times S. S is just a measurement of how much the spring is stretched or compressed, which is just the magnitude of the length of the spring, L minus L naught, which is the relaxed length of the spring. And all of that times L hat, which is just the direction the force is applied. So we use that to then derive the velocity and position update formulas for our code. And within the energy principle just states that the change in energy of the system is equal to the work done by the surroundings plus Q, the heat transfer. And so we know work done by the surroundings is just a change in kinetic energy plus a change in potential energy. There were two potential energies in this system, the spring potential energy and the gravitational potential energy. So you just add that up with the change in kinetic energy to get your change in energy of the system. So before we could do anything, we needed to use Tracker to analyze the x and y positions of the mass over time and find the period t. The period is just how much time it takes for one oscillation to occur. So we wanted to find the average of that by summing the time over multiple oscillations and dividing by the number of oscillations that occur. So the period we found, the average period was 1.5195 seconds. And so what we also know is that t, the period, is equal to 2 pi times the square root of m over the spring constant. And the reason why we need to know this is because we need to find the spring constant and find L naught. So, knowing this, we can just solve for the spring constant, which we did to find it as 6.87 newtons per meter. For L naught, we needed to set up F net as with equilibrium, where F net equals 0. So therefore, the force of the spring should be equal to the force of the gravity, since those are the only forces acting on them, but in the opposite directions, of course. And so we know that the initial length of the spring was 0.7 meters down from the fixed attachment point. So we could then therefore solve for L naught, just like that, to be 0.126 meters. So for further initial conditions for the energies, we just initialized the different energies, the kinetic energy, potential energy, gravitational potential energy, and then spring potential energy, and added those together to get the total energy. So finally, we can, for our loop now for the code, we could then, we needed to define initial energies, which are just the exact same thing as before, I just said. And then from there, we needed to find F net. So we just found F grav and F spring, added them together, F net. And then using F net, we could then update the mass's velocity and the mass's position, which is important because from there we needed to use that to update the spring potential energy and all of the energies, the kinetic energy, the spring potential energy, and the gravitational potential energy as so. And then using those updated energies, we just subtract them from the originals to then find our changes in those energies and in the total energy of the system. And so from that, we found that the total energy, the change in energy of the system was equal to 0, which makes sense because the code only accounted for the changes in energy within the system. And so it's an isolated system, so therefore no energy exchanges happen. We also looked at the model versus experimental y position oscillations and the x position oscillations. So for the y position oscillations, you can see that the amplitudes of the experimental data are smaller than the model, and you can also see that the amplitudes seem to get smaller, starting at around 7 seconds, which is interesting. So for x position oscillations, it's pretty much the same with amplitude. It's relatively consistent the whole way through. However, you can see that here the curve starts to get misaligned, which is a bit weird, but happens. So to discuss, as I said before, it was an isolated system, but in real life, the mass Earth spring system is not isolated, and energy is exchanged between the system and the surroundings. Therefore, dissipated forces, like air resistance, or even the friction between the spring and the attachment fixture, could cause heat to be released from the system, therefore decreasing kinetic energy. And so this may explain why the amplitude on the experimental y positions decreased as time went on. Of course, some of this error could also just be due to tracking from the tracking in tracker of the positions. So finally, we wanted to compare the periods of oscillation of the experimental data. So we estimated the x position period was 1.662 seconds, and the y position period was 1.5195 seconds, which is the same as we used for the whole experiment. So this suggests that because they are different periods, it suggests that there must be different spring constants applied in the x and y direction. But how can this be? A spring should only have one spring constant, which is not dependent on how the spring is oriented. However, in this case, because the stretch of the spring is much greater in the y direction than the x direction, the spring constant has a greater effect in the y direction than the x direction, which that causes the period of oscillation to be smaller in the y direction. So in conclusion, in an isolated system, energy is conserved based on the energy principle, and there may be different effective spring constants in the x and y direction for a spring oscillating at an angle. Thank you very much.